So we established that if we take the set of all translations, rotations, reflections, and glide reflections of the plane with operation, the product operation that we've talked about, that is a group, okay? We call these these are all motions, and we will call them Euclidean motions for reasons that we'll discuss in just a second, okay? So, as I briefly mentioned, Felix Klein was a mathematician in 1872. He classified geometries by saying a geometry is the study of invariant properties, so things that don't vary, of a set of points under a group of transformations. Okay? Now, we can define a number of geometries in this way. Euclidean geometry, it just so happens that if we take this group of Euclidean motions right here, and we look at the set of invariant properties of a set of points, in this case, the Cartesian plane, under a group of transformations, then we get the Euclidean geometry. And some of those invariant properties, things that don't change, are things like angle measure, right? Parallelism, area, distance, okay? Things like this. And so Klein describes a geometry using this definition that it's this set of invariant properties of a set of points under a group of transformations. So it's one reason why this set of Euclidean motions are so important, is because they can underpin Euclidean geometry. Furthermore, they can be a really helpful approach to teaching Euclidean geometry and understanding Euclidean geometry. So we can change the way we talk about things a little bit, okay? For example, consider this theorem right here, that a point P is on the perpendicular bisector of a segment AB if only if it is equidistant from the endpoints. This is a really useful theorem in geometry. We have A and B, okay? This is an if and only if statement. So if we have this point P, we know that if it is equidistant from A and B, then it must lie on the perpendicular bisector, and vice versa. If it's on the perpendicular bisector, it must be equidistant, okay? So that's helpful, and we can prove this. We can do some stuff with congruent triangles to prove this. It's a really nice Euclidean geometry result, and not too bad to prove. But we can also think about it in terms of transformations, right? We can say point P, so instead of the theorem the way we've written it, we could say point P is on the perpendicular bisector, I'm going to abbreviate, that's all right, of segment AB if and only if A and B are corresponding points in a reflection about a line through P that is perpendicular to AB. Okay? So in other words, instead of thinking about this in terms of the pieces here, we think about it in terms of a transformation. We say, we know A and B, so we have this segment AB right here. We say P, this point P is on the perpendicular bisector if there's a line through P that is perpendicular to AB where we can define a reflection where A and B are corresponding points. And now that gives us some stuff like if these two are corresponding points over this reflection and the lines through P, then these are corresponding lines, and therefore those lines must be congruent. Okay? We don't necessarily have to prove that in order to prove our theorem, but that's kind of what we get for free. We're getting at the same ideas here. Basically, we define like congruence as correspondence under some rigid motion. Okay? So we can kind of rethink how we talk about things. Similarly, like if you take the result that's like the diagonals of a of a parallelogram bisect each other. Okay. Again, really nice Euclidean idea. Here's a parallelogram. Well, not a very good parallelogram, but we're going to say diagonal, diagonal, and then this has to be that, and that has to, like so. Okay. Again, you could do this with like vertical angles. Those are got to be congruent. These two have to be congruent. If you can prove that opposite sides of the parallelogram have to be congruent, maybe you can get some stuff working from that. You know, these are parallel, so you get these angles must be congruent. You can do some, kind of point chasing here. Or another way to do it is to say, all right, here is a parallelogram. Okay. Let's look at these right here. Okay. So let's let this point P be the center of a rotation of 180 degrees about P. Well, what's going to happen under that rotation is this is going to correspond with this, right? And this is going to correspond with this. So therefore, that they must be congruent, right? Corresponding parts must be congruent, and so therefore the diagonals must bisect each other. Because this has symmetry and will lie on top of itself under 180 degree rotation. Okay. So it's just another tool to have at our disposal and allows us to prove a lot of things just using transformations. Okay. Yes, just using transformations. In particular, these Euclidean motions. So what I want to talk about with these Euclidean motions is their equations. Okay. So we're going to talk about the equations of translations and rotations today, and we'll talk about reflections next time and discuss glide reflections as well. So a translation, remember for a translation we define it's by a vector AB. So this isn't too bad. If you have a point xy, and you want to translate it by a vector that has these components a and b, well, this is just going to be x plus a and y plus b. So the equation here is x prime our image. Okay, so x prime, y prime is our image here. X prime is just x plus a. Y prime is just y plus b. Okay. So translations, not too bad. Just adding stuff, okay? Now let's think about rotations. So secondly, rotations. Well, let's start with the easy case, okay? Let's start with a rotation counterclockwise. Actually, I'm going to leave off counterclockwise because remember we're going to assume that if it's a positive angle, it is counterclockwise. And if it's a negative angle, then it's clockwise. Rotation by an angle alpha about the origin. Okay. So if we have a rotation by an angle alpha about the origin, think about what's going to happen here. So we have this point xy, and we're going to rotate it, and I'm going to kind of just draw this right here. We're going to rotate it by some angle alpha, okay, to out here, x prime, y prime. Now note that these distances from the origin must be the same, so we'll call it r, and so these two have to be the same. And we're going to say this is the angle alpha. Okay. Well, let's say that this angle right in here, that this original angle is just beta. Okay. So what we know is that if we look at cosine of beta, it's just going to be x over r, and sine of beta is y over r. So x can just be written as the original first coordinate can just be written as r cosine beta, and y can be written as r sine beta. Okay. Well, similarly, if we look out here at x prime, y prime, x prime should be r cosine of the sum of those two angles, alpha plus beta, and y prime should equal r sine of alpha plus beta. So in order to simplify this, we know that we have angle sum formulas, which if you have forgotten those, this is your opportunity to look them back up. Okay, so angle sum formulas, we just make a little substitution here and we say x prime equals r. The sum formula for cosine is cosine alpha cosine beta minus sine alpha sine beta. And for y prime, it is r cosine alpha sine beta. Oops. Cosine alpha sine beta plus sine alpha cosine beta. Okay. And then we just do a little simplification. We multiply through, we're going to get r cosine alpha cosine beta minus r sine alpha sine beta, x prime, and then y prime is r cosine alpha sine beta plus r sine alpha cosine beta. Now, remember that we have these equations right here, right? So if we have r times sine beta, that's just y. If we have r times cosine beta, that's just x. So here we have r sine beta, r cosine beta. So if we make those substitutions, then we see that x prime should equal r cosine beta is x, so we have x cosine alpha, minus r sine beta is y sine alpha. And y prime is going to be r sine beta is y plus r cosine beta is x. Okay, and there we have it. Okay. So these are the equations for rotation by angle theta about origin 0, 0. Okay. And I'll leave it to your problem set for you to experiment with this a little bit, and you can see, plug an angle in, and you can see that this works. So the question here becomes like, what if we have a rotation about a different point? So if we want to rotate by an angle theta about a point other than the origin, let's say HK, how are we going to handle that? Well, here we need to think about a few, the product of multiple transformations. So I know how to rotate about the origin. Let's say I want to rotate around this point HK, okay, by an angle theta. Not theta, but alpha. Okay. Well, what we're going to do here is just think about it this way. I'm going to take my whatever point I have, right here, and everything. I'm just going to move everything the center of rotation to the origin. All right. So I'm just going to rotate, or just going to translate all my points so that my center of rotation becomes the origin, and then I'll translate back. Okay. So translate. So center of the rotation is 0, 0. And so in order to do that, we just have to subtract h and subtract k from everything. So x prime is going to be x minus h. Y prime is going to be y minus k. Okay. All right. Then we perform our rotation. So rotate by alpha about the origin. Okay. Rotate alpha about the origin. So what we're going to do there is now we'll have like x double prime. We'll just take the image from the first one here and plug it in to the formulas we just found. Okay. Well, I've run out of room here, so I'm going to kind of come over here to finish this off, and then we'll get a new page. So if we just go back to our original here, x prime is just x minus h. And y prime is y minus k. And so we get these right here. Oops. Okay. So then the last thing we're going to do is we translated this everything so the center of rotation was the origin. We did our rotation, and now we need to move everything back. Okay. So our third step is to translate. So center of rotation is HK. Okay, so I'm just going to translate by that vector. So x triple prime is just going to be the second image plus h, and y triple prime is just going to be the second image plus k. And so we get that the final result is x minus h cosine alpha minus y minus k sine alpha plus h, and the image of y is going to be, to follow what we had earlier, y minus k cosine alpha plus x minus h sine alpha, and then we're going to add k to get that. Okay, so by the way, usually we write this as x minus h sine alpha plus y minus k cosine alpha, which is not what I did earlier, but it should work. Okay, so the final answer here is that to rotate the equations, to rotate by angle theta, or not theta, alpha, about hk, we get the equations x prime equals x minus h cosine alpha minus y minus k sine alpha plus h, and y prime equals x minus h sine alpha plus y minus k cosine alpha plus k. Okay, beautiful. Okay, this is quite lovely. Now, one nice thing about this, before I let you go, is that if we have rotation about the origin, so that was an example we talked about earlier. So the easy case, if we have rotation about 0, 0, that's where you have x prime equals just x cosine alpha minus y sine alpha, and y prime equals x sine alpha plus y cosine alpha. Well, we get a really nice thing here in that we can rewrite this in vector notation if we really want to, and say x prime y prime is going to equal cosine alpha negative sine alpha cosine alpha times the vector xy. Okay, so we can actually use this matrix notation for thinking about that a little bit. Okay, that's helpful. And then we can build a matrix, and then we can just multiply it by any. It's a nice way to automate this, by any vector for any point, and get the output quite easily. Okay. All right. This again, if you didn't follow any of that, this is your responsibility on these videos. You need to stop, listen to them actively. So be writing down as you go along, taking notes, go back, rewind, make sure things make sense. Okay? And next time we will talk about how we define the equations of a